In this video we're going to look at higher order partial derivatives. So let's say you've got a surface looking like this, and if you treat y as a constant, meaning you've got this this plane along the y-axis here. Hang on, let me just draw this plane. So when you treat y as a constant, so hang on. So the origin is right at this dot here. So if you treat y as a constant, so this is y equals 1, y equals 2, y equals 3, and so on. If you treat y as a constant, this vertical plane, where it intersects with a surface, it will give you something looking like this. So if you treat y as a constant, you're really taking the partial derivative with respect to x. So you're going to get a series of these intersection of the vertical plane and the surface. It will look something like this, and the equation for this would be of this form. So this thing here is exactly the same as this. It's just two different ways of writing the same thing. So when you have a surface looking like this, if you treat y as a constant, you're really taking the partial derivative with respect to x. So it will give you this. Now there's no reason why we can't differentiate this curve again. So when you differentiate it again, so you're going to have something like this. So you're differentiating it with respect to x again. So this would be written as this. The notation for it would be x. So you would do this first, and then you would do this. So it would be xx. So really, when you come to differentiate this, you're differentiating it again with respect to x. So this whole thing here is a constant, so it would be 0, and then differentiate it with respect to x. That will then give you negative 6xy. So the second derivative, the second partial derivative, will be given by this. So now, if you look at if you treat x as a constant, so now you're differentiating with respect to y. If you treat x as a constant, it will look something like this. Remember, this is your x-axis. This is 1, 2, 3, 4, and so on. This is negative 1, negative 2, and so on. If you treat x as a constant, it will mean this. You've got a plane looking something like this. So this is your vertical sheet of paper here. The origin is right here, somewhere around here. So if you treat x as a constant, you're really moving along like this, or in the negative direction like this. So where the vertical sheet of paper intersects with the surface, it will give you something looking like this. So you can differentiate. You can take the partial derivative of our surface with respect to y when you treat x as a constant. So it will then give you this. Now what I'm saying in this video is that you can take the derivative again with respect to y. So you can actually do this. Differentiate it again with respect to y. So it would be like this, and it would be written as this. Z, y, which is this thing here, and then you're differentiating it again with respect to y. So that will then give you this. So now looking at this, differentiate it again with respect to y, that will then give you 4x, and this is just a constant. So it will then give you this. So what I'm saying here is that you can differentiate this again. So you can differentiate it twice. So overall, if you differentiate it once, if you have a function, you can differentiate it once. That will then give you this. Differentiate it again with respect to y, it will then give you this. So if you have a function, if you want to differentiate it twice, then it would be written as this. And then if you want to differentiate it twice with respect to y, it would be written as this. Y. So really here you've got to do this first and then this. Okay, and also you can differentiate. You can take the partial derivative with respect to x first, and then with respect to y, and then this will then be written as this. So when you see this, you're actually doing this thing first. You're taking the partial derivative with respect to x first, and then you do the y, and then you do the y. So when you read this thing here, you've got to do this first, x first, and then the y. And when you see this, in your mind, you've got to picture this first. So you've got to do it with the x first, and then the y. And the reverse is also true over here. So when given this, looking at this, you in your mind, you've got to picture this first. So you do it with respect to y first, and then x. And then when you see this, you've got to do it with respect to y first, and then with respect to x. And something that you have to accept for the time being is that know that it doesn't matter which order you do it in first. These two will always be the same. So let me illustrate it. Looking at our surface. So looking at this, it doesn't matter if you do x first or y first. The two final results will be the same. So let me illustrate it with our surface. So let's do this with respect to x first. So looking at the surface, differentiate it with respect to x first. That will then give you this. So we've done this already. Now looking at this, differentiate it again with respect to y. So looking at this, the 2 will come down. So that will give you a 4, and then the y's there. And then differentiate this with respect to y. This whole thing here is a constant. It will then give you this. So one journey would lead us to this. Now let's look at this journey. So let's do it with respect to y first, as opposed to x. So let's do it with respect to y first. So looking at this, y's are differentiated with respect to y. That will then give you this. And then we've done this already with respect to y. Now differentiate it again, but with respect to x. So when you differentiate this, it would just give you 4y, which is this. Differentiate this with respect to x, so the 3 will come down, and then x stays the same, the power gets minus by 1, it will give you this. Notice that this is exactly the same as this. What I'm trying to illustrate here is that it doesn't matter which order you do it, the two will be the same. Okay?